Okay. So in point one, we have the three problems on your finish off that time. If that time period, the time length differs, then how to handle. So this is the ordinary one. Here the way you define is slightly different. Okay, so the next example, so we have three more examples on this. After that, we can move on to. Number of road construction projects. On a particular topic, because this time is difficult to complete for last hypothesis testing, the problem sheet, plus the lectures I have uploaded. I'm already lazy. So we discuss this Poisson. If a variable is defined in two patterns, then it belongs to Poisson. First one is number of occurrences during a fixed period. Number of occurrences during a fixed period, then it is Poisson. Or else number of items in a fixed volume or area. Right? Okay. So now here, to answer this question, how we should define the variable. It should here for that. How we should define here. They have given like the number of road construction projects that take place at any one time in a certain city follows a Poisson distribution with mean 3. Find the probability that exactly 5 road construction projects are currently taking place. Right, so in order to answer that question, how we should define the X? So anyway, it starts with like number of, okay. Try the other one, doesn't matter even if you make mistakes, it's okay, fine. Number of construction project, okay. So that is number of occurrences. ඊට පස්සේ ඕන fixed period. So in this one, how do we take that fixed period? 10 minutes, 1 year, 1 month, right? Like that. How we take here? At any one time. Right? So something like that, right? At any one time, right? At a particular time, right? Okay. So here we define, so this is different from what we discussed earlier. Earlier we said, okay, what is number of accidents during a month, number of people joining a queue in 10-minute interval. So we had a fixed period. Now here we don't have a time. So here we say at any one time. So here the variable should be number of road construction projects at any one time or at a time. Okay, that's how we define here, right? Okay, right. So we'll define that way. So X we can define as number of road construction projects at a time, you can say, or at one time, also fine. At a time of at one time. So the average is given lambda is 3. Right. So lambda is 3. We know this is going to be Poisson. So X follows Poisson with 3. So next we write down the probability function. So recall the general probability function and apply and get your probability function. Probability capital X equals simple X. E to the power of minus lambda to the power of X over X factorial. Then we put the colon and mention what are the values this X can take, 0, 1, 2, 3, and so on. A variable defined, parameter identified, distribution identified, probability function written. So first they are asking us 7 of first 5 more than 3. 5 projects. So first part, probability. X equals 5. So we take this expression, substitute 5. Evaluate. So we learn how to evaluate. Get the answer 4 decimal place properly rounded. can remember one. Combination, A combination, so it is shaped. If ln minus d b to the power of the power of 5 division 5 factorial, so 5 factorial shift x inverse, and then finally equal heat will give you the next one. Okay, so answer for this one. Okay, one. So always when you evaluate, try to evaluate at once. Otherwise, this will be a small value. This will be a large value. So if we round off this one, then there will be a huge hit. So try to evaluate at once like this. And finally, only once you are rounding off, so that rounding off errors will be reduced. So next one, more than 3. The second part, probability, number of construction projects, more than or equal, just more than, right, more than 3. Right. So now, when you have more than or more than equal in Poisson, you can't directly calculate because it will go up to infinity. You can't calculate, so always we go for the reverse. So we'll write the reverse of this. 1 minus probability x less than or equal to 3. Original one doesn't have the equal sign, so the reverse will have the equals. So what are the possibilities for the second component? Here, equal 1 minus possibilities. So here, x can be 0, plus x can be 1, x can be 2, plus x can be 3. So individually we evaluate, subtract from 1, we get the answer. So the individual required individual values are here by substituting in the formula. Then 1 minus 6 will be here the corresponding values are there. Second one, third one. 4 values you add, subtract from 1. Now we are slowly moving on to the next category, right? Like second version. Number of items, even its volume type. So it says a 5-liter bucket of water is taken from a swamp. The water contains 75 mosquito larvae. A 20 milliliter flask of water is taken from the bucket for further analysis. What is the expected number of larvae in the flask? Expected means average number. Average number. Expected value means average value. Right. So now how can we get that? So now that one says 5-liter contains 75 mosquito larvae. Flask has 200 milliliters. So if 5 liters has 75, how much will be there in 200 milliliters? So 5 liters, 5,000 milliliters has 75. So 200 milliliters, how many? Okay. Right. Five liters has 75. So here that is in milliliters. So we'll convert this into milliliters. So 5,000 milliliters has 75 mosquito larvae. What we have is 200. So in 200, I write here, in 200 milliliters, how many are there? So how the equation goes? 75 over 5,000 into 200. So 75 over 5,000 into 200. How can we simplify? So here 2 zeros. Right, these 2 zeros we can cancel with. So these 2 zeros goes off with these 2 zeros. These 2 we can cancel with this 50. So we get 25. So these 25 and this 75 3 times. So the final answer here is so that is in the flask, average number of larvae is 3. The next part they're asking us, what is the probability that flask contains at least 1? Flask contains at least 1. So to answer this probability problem, we need to define the x because we haven't defined the x. So to answer this question, how we should define the x? Probability that flask contains at least 1. That is what we want to answer. So how we should define the x? Number of mosquito larvae in the flask. Okay, right, okay. So in the flask, but if we define that way, it doesn't fit into any of the model, neither. Right? Model, so flask, what is the volume? 1. So instead of saying flask, 200 milliliters. Number of mosquito larvae in 200 milliliters. Then it fits into the second block. Okay? Right. Okay. So X is number of mosquito within 200 milliliters. Lambda, already we have found that as 3 first part. Then this X follows Poisson distribution. Probability function we have the probability of X equals e to the minus 3 to the X over X factorial. What are the values X can take? 0, 1, 2, and so on. So what are they asking us? So they are asking us at least one. We want probability X greater than or equal to 1, at least 1. So greater than probability is difficult for us to find in Poisson, so we go for the ratio. 1 minus probability X less than 1. The only option here is X is 0. Is 0 means the formula is there, we can calculate or calculate the net. 1 minus 0, 4, 9, 8. 0, 1, 9, 5, 0. For the second category, we said either number of items in a fixed volume or number of items in an area. So this is the second type, number of items in an area on a page. It is observed that there are 2 misprints on average in a page. What is the probability of 7 misprints on a page? What is the probability of at least 4 misprints on 2 pages? Okay. Now tell me, to answer this first part, how we should define the variable? Number of missprints on the page. Okay. So number of misprints on a page. So we are answering the first part. X is number of misprints on a page. Right. So the average number of misprints on a page given 5. So lambda is 5 here. So we can say, according to the way the variable is defined, this is going to be a Poisson variable with 5. Now we can write down the probability function. So PR x equals x. E to the power of minus lambda, lambda to the power of x over x factorial. What are the values x can take? X can be 0, 1, 2, 3, and so on. So what are they asking us? The probability of 7 misprints. Right? So they are asking us probability of capital X number of misprints equals 7. E to the minus 5, 5 to the 7 over 7 factorial. Of course, you know how to evaluate. If you get the concepts properly, then the things are easy, right? Second part, probability of at least 4 misprints on 2 pages. So can we answer that question with this variable? This is for 1 page. So 2 page, now that category is different. Everything should be done from the beginning. To define the variable accordingly, lambda should be identified, probability function should be identified. Using that one, so to answer that second question, how we should define the variable? At least 4 misprints on 2 pages. So how we should define? Number of misprints on 2 pages. Lambda will be per page. What is the average? 5. 2 pages? 10. You just double it. Okay. Half a page now. Make it half. Okay. Right. So when that level difference is there, then the entire thing should be done from the beginning. You define the variable, identify the parameter. Now x should be second part. X should be number of misprints on 2 pages. Lambda per page 5. Now we are looking at 2 pages, so it will be 10. Now this x is supposed to follow Poisson distribution with parameter 10. So accordingly, the probability function. So probability capital X equals simple X. e to the minus 10, 10 to the x over x factorial. What are the values x can take? Can be 0, 1, 2, 3, and so on. So what are they asking us? They are asking us for at least 4. So we want to find probability at least 4. X greater than or equal to 4. We can't go for this, so we take the reverse. 1 minus probability x less than 4. So we have 4 possibilities here. 1 minus probability x can be 0, x can be 1, x can be 2, plus x can be. Then you subtract, find the values. The individual values of each one is here. So here I have just dragged, you need only up to third level. When you calculate sometimes, make it 2 point and then make 2 point something. 2 point something, but into 10 to the power of -4 -5. So accordingly, you have to shift the decimal. First 4 digits you take. Right. So in this problem, there are 4 parts. So I have highlighted all the 4 parts separately because the time duration changes. See here, this is some probability during next month. This is during the next 2 months, during the next 2 years, during the next half a month. So the time level changes. So when the time level changes, full process you have to do. For this one, you have to define the variable lambda, you have to find probability function, then you calculate. For this one, again, you do the same thing with according to for 2 month period. Okay, take it down after. So this is also something similar to the second part of the previous problem, right? So here it is defining the first category, right? First category, but when the duration changes, how you handle it. There were 30 power breakdowns during the last year in an urban area. What is the probability of 4 breakdowns during the next month? Now here, during the last year, 30 breakdowns per year. Now, if you look at the, now, always when we define the variable, we have to look at the question, and according to the question, we have to identify the variable. So now, what is the probability of 4 breakdowns during the next month? So to answer this one, how we should define the variable? Number of breakdowns. Yeah. Yeah. So now we don't have to say next month, just next month. Sorry, just month, right? Per month, number of power breakdowns per month. So it can be, we can answer next month through that, or previous month through that, or maybe the month after next month we can define. So if we just define as month, that's enough, right? Only the period needed. So number of power breakdowns per month. First part, X is number of power breakdowns, number of breakdowns per month. Number of happenings during a fixed period, first category. Right. So now lambda, since we have defined as per month, lambda should be per month value. In a year, 30. So per month divided by 30. So 30 per year, we want the monthly one, so we have to divide by 12. So 2.5. X follows now Poisson with 2.5. So we can write down the probability function now. Probability X equals X e to the power of minus 2.5, 2.5 to the power of X over X factorial. So X can be 0, 1, 2, 3, and so on. Variable identified, parameter identified, distribution identified, probability function rating. Now we can answer it related to that. How many does he for that? 4, exactly 4, right? So we want to find probability X equals 4. Probability X equals e to the power of minus 2.5, 2.5 to the power of 4. But 4 factorial. We can get it. same. Thirteen 36. Next. The next one, at least 2, 3, next 2 months. Second part, it's the number of power breakdowns in 2 months. So lambda need to be found. So per year 30. If you divide by 12, we get the 1 month rate, but we want the 2 month rate, so multiply by 2. So it is 60 over 2, sorry, 60 over 12, which is 5. So lambda is 5. Now this X follows Poisson with 5. So we can write down the probability function. PR X equals X. E to the minus 5, 5 to the X over X factorial. What are the values X can take? X can be 0, 1, 2, 3, 4, and so on. So what we want is at least 3. Is 3. We want probability of X greater than or equal to 3. So we go for the reverse. Probability X less than 1 minus. Probability X can be 0, X can be 1, or X can be 2. The values are there. These 3 values, add and subtract. Next one, 45 breakdowns during the next 2 years. 2 years, 45 breakdowns. Third one. Number of breakdowns during 2 years. So lambda per year 30, 2 years, so it is 60. So probably x follows Poisson is 60. So the probability function Prx equals x e to the minus 60, 60 to the x over x factorial. X can be 0, 1, 2, and so on, blah, blah, blah. So they are asking for 45. So x equals 45. Only one value. The power of minus 60. 60 to the power of 45 over 45. When you simplify, sometimes you may get this answer like 7.6 blah blah. In some old calculators, you will be getting like E minus 3. So in new calculator, you will be getting like 10 to the power minus 3. So you have to read with this part. So minus 3, E minus 3 or 10 to the power minus 3 means you have to shift this decimal towards the left by 3 levels. So 0, 0. So 3 levels, 1, 2, 3. Right now the dot comes here. Last part of this. At most 3 during next half a month. Half a month. But exceeds number of power breakdowns during half a month. During half a month. lambda value, right? So per month, per year, it is 30, half a month. So you have to divide by 24. Or maybe per month rate we have calculated as 2.5. So that 2.5 you divide by 2 also you get, right? So 30 divided by 24. 1.25. So X follows horizon with 1.25. So probability function Prx equals e to the power of minus 1.25, 1.25 to the power of x over x factor. So x can be 0, 1, 2. They are asking for at least 3. At least 4. Oh, at most 3. So we want probability of x less than or equal to 3 at most 3. So what are the possibilities? X can be 0, x can be 1, x can be 2, or x can be 3. So each one we have to evaluate and then give the answer. Right. Right. So that concludes points on this. We have done all the types, right? So that in formula we can do it, right? Okay, next we'll move on to the next type, normal distribution. So binomial discussed, Poisson discussed, both are discrete type. Because it takes like values 0, 1, 2, 3, so discrete type. Now this is a continuous type. So the topic has subtopic as binomial distribution. Distribution. So initially we have to write a bit, so we write that. Most of the most of the variables, we come across. Most of the variables we come across in day-to-day life. Most of the variables we come across in day-to-day life are normally distributed. In day-to-day life are normally distributed. First up, continuing. The following are some of the variables. The following are some of the variables. The following some of the variables that are normally distributed. Following are some of the variables that are normally distributed. Right? So why am I giving you this list is in a problem, if they talk about one of these variables, they won't tell you that it is normally distributed. We have to know that it is normally distributed, right? The lifetime, marks, if they are talking about those things in a problem, they won't tell you that this is normal variable or normally distributed, right? Otherwise, if they talk about a new variable, then they will tell you this is normally distributed or approximately normally distributed. They will tell you, right? So these are the ones. So we'll write it as bullet points. Lifetime, first one, lifetime. Lifetime is a normally distributed variable. Lifetime. So when you say lifetime, it can be lifetime of anything. Lifetime of human beings, lifetime of animals, lifetime of buildings. Lifetime of anything will be normally distributed. Lifetime of bulbs, electronic items, all are normally distributed. Second one is marks. Marks of students. Marks of students in a class. O-level marks of a particular year. Marks of students in a school, normally distributed. Right? Marks is a normally distributed variable. Income. Income is a normally distributed variable. Income. Right? Income of people in an area, normally distributed. right? Or income of Sri Lanka. Is it a variable per month if you take? Not a variable, right? Income of countries in the Asian region. That is normally distributed because you have so many values, right? Income of Sri Lanka give with only one value. Okay, so it should be a variable. Many values should be there, right? Income of households in a particular region. Income of countries in the Asian region or European region, whatever. Then height. Height is a normally distributed variable. Height. If you take height of students in a class, normally distributed. Height of students in a class. Height of buildings in an area. Height of buildings in an area, normally distributed. Is a normally distributed. Then weight. Weight of students in a class, normally distributed. Weight of students in a class, normally distributed. Weight of people in Sri Lanka, normally distributed. Weight of people in Sri Lanka. So, yeah, that's a normally distributed weight, right? And then the weight. Similarly, if you take length also normally like this, say. Now consider a mass-produced item like reinforcement bars. Reinforcement bars, if you take, okay, say 19 feet or something, they say. But if you take a length and measure, it won't be 90, right? Maybe 18 or it may be 19.5, right? So the length of iron rods varies, right? But that is normally, right? Length of mass-produced item normally distributed. So weight, length, height, income, marks, lifetime, all these are normally distributed. So mostly either lifetime or marks, height or weight, if they give you, then you should be able to identify that it is normal variable, even if it is not given. Right? The next, a small, right, characteristics of normal distribution. Characteristics of normal distribution. Characteristics of normal distribution. I will now it is clear. Characteristics of normal distribution. So you have to draw a horizontal line. Then this bell-shaped curve. So when you draw this curve should not touch this line at both ends, right? It gets closer and closer, but doesn't touch. Right? Then exact middle, a line, mu, and two more lines here. In between area highlighted, A, B, simple is. When you draw, that should be symmetric, right? So we'll write down. So we'll write it as bullet point. Bullet points of say 1, 2, 3, whatever. Right. So the first one. This is a bell shape, BPLL, bell shape. This is the first one. This is a bell shaped, SHAPE shape, bell shape, symmetric distribution, bell shape, symmetric distribution about the mean, mu notation, actually notation mu, you know, about the mean mu, right? So see, bell shape, symmetric. So right here, if you fold this structure, this part comes and points in. So I did that, right? So symmetric structure. So that's the first one. Bell-shaped symmetric distribution about the mean. Second point, second bullet point, right? The total area under the curve, is 1, value 1. So earlier we said, okay, total area under the curve means the area under this curve and above this line. So this area is 1. Earlier we said this is symmetric. So this is 0.5. This area is 0.5 and this area is 0.5, right? Full area is 1, symmetric. So this is 0.5 and that is 0.5. Second. Then third one, the shape of this distribution, shape of the normal distribution, put it that way. The shape of the normal distribution, is given by the probability density function, PDF. So in short, we call this as PDF, probability density function, PDF. So what is that PDF function? Right. Given by the probability density function, right? Fx equals, right, 1 over 2 pi sigma squared square root e to the power of e to the power of minus half x minus mu over sigma whole thing square. 1 over 2 pi sigma squared square root e to the power of, e means that same e, Poisson-Molina same e to the power of minus half x minus mu over sigma whole thing square. So then we have to say, no need to memorize these things, right? So what are the values this x can take? We write here, the space Madinda, right there, put the colon. Then this x can be any real value between negative infinity to positive infinity. So x lies between minus infinity and plus infinity. So this is infinity. So infinity you write like 8, turn to the other side. and here there is a small gap. Put gap on. Like this. 8 turn to the other side, so there is a gap in between. So there is a tool also. Okay, don't write like this. This is different. That is alpha. Right? This is alpha. This is it. So here this should come minus infinity. Right? So that is the function which gives that shape. You better write it in one line. I think that I wrote it here. So this, if you can write there, it's better. So just to have an understanding, right? To give that shape, okay, that's a function. No need to memorize this function. That's the third point. So now the fourth point. Fourth point. The probabilities of a normal variable. The probabilities of a normal variable. Probabilities of a normal variable. Probabilities of a normal variable. Are given by probabilities of a normal variable are given by the corresponding are given by the corresponding area are given by the corresponding area as shown in the diagram. Given by the area as shown in the diagram. So now see here we have highlighted the area. Here we have written A, here we have written B. So in this diagram, if you write anything, a number below this line that refers the value on this line. So here this value is A, this value is B. So which area highlighted? Above A and below B we have highlighted. So this region represents the corresponding probability. So this highlighted region represents probability A less than X less than B. So this highlighted area represents this probability above A, below B. Small value first, then the X, then B. So if you want to find the normal probability, then you find the corresponding area. That's all you do because the area is equivalent to the probability. So now always we compare and do the learning, then it's easy. Now when we discuss binomial Poisson, we identify how many parameters are there. Then how to denote the binomial variable. those things we discussed. So here also we have to see normal variable, how many parameters are there, what are the parameters, how do we denote a normal variable. So we'll discuss that next. Next para, write down. To identify, next para, to identify a normal variable, to identify a normal variable, we need two parameters. To identify a normal variable, we need two parameters. Namely, the mean mu notation. The mean mu and the standard deviation sigma notation. Mean mu and the standard deviation sigma. Normal variable has normal distribution has two parameters, mean and the standard deviation. So next, how do we denote this? Right. The next line, let x, capital X, let x be a random variable. Let x be a random variable following, let capital X be a random variable following normal distribution. Let x be a random variable following normal distribution with parameters mu and sigma. Notation done. With parameters mu and sigma. Then it can be denoted by. So now what do we want to denote? X follows normal distribution with parameters mu and sigma. Right. So X, okay, random variable X follows what? Normal. Binomial we write bin. Poisson we write PO or POI. Normal we write only one letter, capital N, because it's special. So follows normal N. Then the two parameters should go inside the bracket. So bracket, the two parameters will come up. First we write the mean value. Then we write the sigma squared value, not sigma, we write the sigma squared value. Standard deviation squared. So standard deviation squared is variance. So sigma is standard deviation. Sigma squared is variance. So here in the notation we write variance. Right? Sigma squared value we write. Or say standard deviation 5, then we write 5 squared. So now don't write this. Now suppose you come across something like this. X, you will get a notation like this, X follows N, 75, 25. So what do you understand from this? X is what type of variable? Normal variable. What is the mean? What is the standard deviation? So it is 5, right? Not 25, it is 5, right? Because here we write 5 square, sorry, sigma square. Right. So we can continue next para. Next line, you can write the mean mu, the mean mu can take any real value, The mean mu can take any real value. While the standard deviation, sigma can take, standard deviation sigma can take any strictly positive real value. Strictly positive real value. Mu can take any real value, minus infinity to plus infinity can take any real value, including 0. But standard deviation can take only strictly positive real value. That means negative values are not allowed. 0 is also not allowed because strictly positive. Above 0, anything is allowed. Right. So in the notation form, if we want to write that statement, right? Mu lies between plus infinity and minus infinity. Mu lies between these two, minus infinity to plus infinity. And sigma is above 0 and below plus infinity. Mu lies between minus infinity to plus infinity. Standard deviation sigma is strictly positive. So above 0, below. So now from this statement, you should be able to imagine mu can have hell a lot of values. Minus 5 possible, minus 5.5 possible, minus 100 possible, 0 possible, 100 possible, 101.2 possible. There are value possible. Sigma, negative values are not possible, 0 are not possible, positive side, any value is possible. So you get these mu and this mu and sigma can have hell a lot of values, right? So now product imagine now I am having a x1, one variable, normal, mean is 5, standard deviation is 2. Possible name? Mu is 5, yes, possible, standard deviation 2, possible, right? I am having another variable, mean is 5, standard deviation is 2.1. Possible. When I have anything, right? Because the standard deviation is different. So this is a normal variable. This is another normal variable. Mean is the same, but standard deviation is different. So I can create another third normal variable. This is 5. This is 2.01 square. Yeah, other than that, second, right? So different. So likewise, now imagine I can keep this fixed by I can change this value. So I get a series of normal variable, right? Okay. If I make a fixed color, I can change this also. Negative values I can have, positive values I can have. Now you feel like you have hell a lot of normal variables. right? You have a huge collection of normal variables, right? Because if this change a bit, right, you get a different variable. If this change a bit, you get a different variable. So you get a huge collection of normal variables, huge collection of normal. So from that huge collection, you take one variable which has the mean value 0, standard deviation value 1. Mu 0 possible there? Yes. Standard deviation 1 possible there? Yes. එතකොට මේ දෙක මේම වෙන එකෙකුත් ඔය pool එක ඇතුලේ ඉන්නව නේද? So I picked that normal variable and I call it as the standard normal variable. Okay, so according to the way this mu and sigma can have values, we get a huge collection of normal variables. So from that huge collection, we pick the normal variable which has the mean value 0 and standard deviation value 1, and we call that as the standard normal variable, and we denote it by Z. Okay. According to the values, according to the values that mu and sigma can take, according to the values that mu and sigma can take, we have a huge collection of normal variables, huge collection of normal variables. First up, from this collection, we pick the normal variable from this collection. We pick the normal variable. This collection, we pick the normal variable, which has the mean, mu equals 0, which has the mean mu equals 0, and standard deviation sigma equals 1, and standard deviation sigma equals 1. Standard deviation sigma equals 1. And call it as the standard normal variable, and call it as the standard normal variable, and we give the special notation, is it for that variable. We give the special notation is it for that variable, right? So in probability, we don't use Z for any other variable, right? Z means it is standard normal. If we come across a Z in probability section, we treat this as standard normal variable. Okay, right. So now this Z means what? Z means normal variable, that is also a normal variable, but it is special. What is the speciality? Mean is 0, standard deviation is 1. So Z follows normal, mean is 0, standard deviation is 1. But here we write sigma square. 1 square, but 1 square is 1. We just write Z follows normal 0. Z follows N 0 1. So Z is also normal variable, nothing else, normal variable, but it is a special case. That is a general one. Mu can be anything, standard deviation can be any positive real. Here, mean is 0, standard deviation is 1, fixed. So now earlier we draw the diagram for the normal variable. Here we wrote mu. Mu means what? Mean of the variable. Mean of the variable. But if we draw the same structure for Z, how would be the structure? General normal. If we draw for Z, structure will be the same structure. I mean, same structure. That point will be okay. It was for the questions. The Z scale diagram. The Z scale diagram. The Z scale diagram will be. The Z scale diagram will be. Structure. This will be Z scale. Same shape. Only thing is instead of mu, we substitute 0 because mu value is this. Z scale structure. And again, X scale structure. Right? X word and now X scale. Z word and now Z scale. The name, right? That's it. Z scale structure. So when we write 0 here, that means if we write any value here below this line, those values refer the values on this line. Or value is 0. Positive values are on this side. Negative values are on that side. So if we write anything below this line, that refers the value on this line. To find the probabilities of the standard normal variable, to find the probabilities of the standard normal variable, find the probabilities of the standard normal variable. Find the probabilities of standard normal variable. We refer the standard normal table. We refer the standard normal table. How do we go for it? Exercise or example. Find the probabilities. Find the probabilities. Find the probabilities using the find the probabilities using the standard normal table. Find the probabilities using the standard normal table. Find the probabilities using the standard normal table. One by one, we'll check. So first one, probability 0 less than Z less than 1.2. One by one will be probability 0 less than Z less than 1 point. Right. So now Z given, Z variable. The first one, probability 0 less than Z less than 1.25. So we are in the Z scale, Z variable. So Z scale, we can draw the Z scale sketch. So we'll draw the Z scale sketch. So Z scale 0 comes in the middle. Then 0 we have to mark. It is already marked. 1.25 we have to mark. 1.25. 0 is here, positive values are on this side, negative values are on the other side. This is positive 1.25, so maybe somewhere there. So we'll draw 1.25. So now which area wanted? Above 0, below 1.25. Above 0, below 1.25. So we want this region. We want that region. Okay, right. So now we look at the table. So if we look at the table, so in the table, you have a highlighted region at the top. Okay, that's clear now. Structure area. Okay, other one is T table. So now here we are given a highlighted region because we can have 3 different types of standard normal table, but we will be using this one. So in this table, 0 to whatever the level referred is highlighted. So that means in this table, middle part of this table, these corresponding areas, highlighted areas are given for different Z values. Right. So now the area we have highlighted and the area here are the same, 0 to 1. So now our value is 1.25. So now 0 to 1.25, what is the area we have? We have to refer. So here 1.25. So the first 2 digits you refer from the leftmost column. So 1.25. So 1.2 you refer from here. And the second decimal you refer from the top. But 1.25. So you refer, what is the value? 39.44. That's the answer. That is the area. That is the problem. Right. So very simple. The first 2 digits. Second decimal you refer from the top. The first 2 you refer from here. 1.2. 39.4. So from the table, it is 39. Probability 0 less than Z less than 1. Probability 0 less than Z less than 1. Z variable, so we can draw the Z scale sketch. Z scale, so 0 comes in the middle. 0 we have to mark, already marked. 1 we have to mark positive, so it will be somewhere here. 1. So we have to refer up to 2 decimals. The first decimal like a leftmost, second decimal like from the top. So we have to refer up to 2 decimals. The method is 1, only 1. 1 means 1.00. Right? So 1.00. So above 0, below 1. So we need this region. Need that region. So we refer the table. How do we refer? The first 2 digits we refer from the leftmost column. And the second digit, the second decimal we refer from the top. That are 1.0. So that is 34. One. That one number have probability. 0.7 less than Z less than 1.5. 0 less than Z less than 1.25. 1.5. Right. So we'll draw the structure first, right? So Z scale, we can draw the structure. 0 comes in the middle. 0.7 we have to mark, right? 0.7. It may be somewhere here. 0.7 කියන්නේ 0.70. Second decimal එක දාගන්න. 1.5 maybe somewhere there. 1.5 means 1.50. So above 0.7, below 1.5. So we want this region. So table gives us from 0 to whatever the level you refer. අපිට ඕන දැන් 0.7 to 0.5, 1.5. So how do we refer? 1.5 you refer, you get this region. 0.7 you refer, you get this region. Subtract, you are done. And this is that. So try to memorize, right? This is what I have. This is what I want. How can I get this from what I have? That way you think then the things are easy. 0 to whatever the level we have, we can refer. So 1.5 we can refer. 0.7 we can refer. Subtract, you are done. So 1.5 you refer. 1.5 means this. 4332. 0.7 2580. So 43,732 minus is equivalent to 0.4332. 4332 minus this minus that. So 0. 2580. Now you can subtract that with us. the next one. Probability. Probability is it greater than 1.96. Probability is it greater than 1.96. Z scale. So we can draw the Z scale sketch. Right. 0 comes in the middle. 1.96 we have to mark positive value, so maybe somewhere there. Right. So now we want Z greater than, so this is 1.96. Z greater than 1.96 means we want this region. But table gives us only this area. 0 to whatever the level you give. Now we want the tail part. But full region is 1. Symmetric. So this is 0.5. So 0.5 minus that one. Right? This part you can refer from the table. This is 0.5. So 0.5 minus this region. I'll give you that. 0.5 minus 1.96 if you refer 4750. So that is 0.0250. Probability is it less than minus 1.96. Is it less than minus 1.96? So, is it scale? We can draw the structure, right? 0 comes in the middle. Minus 1.96 we have to mark negative value, so it will be on the negative this side. Minus 1.96. Is it less than that means we want this region. So we have a left side region. Table again only right side region. But the structure is symmetric. Structure is symmetric. So if you have an area on the right side or the same area on the left side, it will be the same because of the symmetric property. So if you want to refer a left side region like this, what you do is you assume that this is on the other side. Right? So if you assume that you are rotating this part that way, what you get? Okay. We know how to refer this and get the answer. Same answer for that. Right? So if you have a left side region, assume that it is on the other side and you refer. Right? That part you are doing in your mind, right? So this to get this area, you refer 1.96. Then you get this area 0.5 minus. So don't introduce a minus or anything when to get the answer for this. After getting this value, don't introduce a minus or anything because this is a probability value. Area it will be the same area. Right? There won't be any negatives. So left side region, you refer this way, assuming that it is on the other side, you refer. This one, probability minus 1.5 less than Z less than 1.5. minus 1.5 less than z less than 1.5. Z scale, we can draw the Z scale sketch. 0 comes in the middle. 1.5 maybe somewhere there. 1.5 means 1.50. Minus 1.5 will be somewhere here. So we want above this and below that. So we want this region. But in the table, we have 0 to whatever the level we require. Now, this is 1.5. This is minus 1.5. So this area and this area are the same. We can get this area. So what we do, we refer this area, double this. I refer this and that are the same. Make a refer that. Take a medical. You get that because this and that area are the same. So this is 2 times this area 1.5 0 you refer 1.5 if you refer it will 4332 0.43 you can multiply 8664 0.886. Next one, probability minus 2.3 less than Z less than 1.7. Probability minus 2.3 less than Z less than 1.7. Right, so I'm trying to give all the types of references. When you can rely anything. So 0 here, 1.7 will be somewhere there, 2.3 will be somewhere here. So now we want this region. This region needed. So now we can't do the calculation like previous because the areas are different. Either 1.7 you refer separately, 2.3 you refer separately, add the two you are done. One 1.7 you refer, 2.3 you refer. 1.7. 1.7 is 4554. This is 4554. 4554. And 2.3 you refer 2.3. 2.3 0.800. You have your calculation. One probability is it less than 2.75. Is that less than 2.75? See 2.75 plus. Okay, here. Is it less than 2 point? Make it greater than 0. That's nothing like that, right? Above this, below that. So here only below 2.75. So it will be the full left side reason below 2.75. full region. So how do we get this? This area we can refer, and this area, this part we can refer, this part we can refer. What is okay? This is point. So refer to 0.75 and 0.5. So 27.5 if you refer 27.5 or 27.5. I think it's 0, 1, 2, 3, 4, 5, 49.70. Is 0.5 this area plus 49.70, I think. So you are right and give the answer 0.9970. That's it. One probability is that greater than minus 1.25 is that greater than minus 1.25 than 1 point. So Z scale, we can draw the structure. 0 comes in the middle. Minus 1.25 we have to mark, maybe somewhere there. Now which one? Is it greater than that? So we want this region. We want this area. So how do we get this particular area? So this area, we can refer by referring 1.25, we can get this area. That is 0.5. This by referring 1.25, you can get this part, and this is 0.5. So 1.25, if you refer, I don't have space in the agenda. So this is 30. What was it? 39.42 plus 0.5. So that is 0.89. Minus 2.6, less than is that less than 1 point, minus 1 point. Minus 2.6, maybe somewhere there, 2.6. 1.4 minus 1.40. We want in between region, this region we want. We want this region. So negative side, but we assume that this is on the other side and you refer. 2.6 you refer, 1.4 you refer, subtract your time. 2.6 you refer, 1.4 you refer, subtract that. about 8, 9 maybe. Then done the 10. Right. I made them cover right. All the types we have covered. Last one. Probability is that greater than 3.13. Is that greater than 3.13? Is that greater than 3.13? Right. So we draw the structure. 0 comes in the middle. 3.13. So we want greater than, so this region needed. Okay, so no question is repeated. එකම type එකේ දෙකක් හැදුවේ නැහැ. හැබැයි මේ වගේ දෙකක් හැදුවා. මේ දෙවෙනි එක නේද? Greater than 1.96 we did same type නේ. Okay, so what is the why we did this twice? මොනාර වෙනසක් තියෙනවා. So how do we get this answer? From 0.5, we remove this part නේද? එතකොට මොකද පේන්නේ නැද්ද ඔයාලට 0.5 minus when you refer what you get 4 නේද 4.9913 දැන් පේන්නේ නැද්ද මොකද වෙනසක් up to now whatever you values you have referred and the value now you have referred, can't you see any difference? So if you look at the table, when you refer any value above 3, right? When you refer any value above 3, it is given up to 5 decimal place because the differences are very, very small. Because when you consider up to 4 decimal place, sometimes you can't even feel the difference. Right? If you are referring any value above 3 or above, you have to give the answer up to 5 decimal place properly. And if you have only up to 4 decimal place, then okay, you give the answer up to 4 decimal. So this one should be given up to 4 decimal, sorry, 5 decimal. So it will be 0, 0, another 0 and 8, 7. Okay. So all the types we know how to define. Okay. So, but when you take real problems will not be in terms of is it. Table is available for standard normal. Real problems will be general normal. A table we can refer to general normal. We have to transfer to standard normal. So how to transfer? We'll discuss. So I have uploaded a probability problem sheet also. Print then we don't have to write the questions. Straight away we can just